My name is Kyuhan. I'm going to talk about source compression technique for deep learning-based computer vision application. This is joint work with my colleague Xiaofeng Si at Hewlett-Packard Labs. DL-based computer vision for IoT devices actually has a huge market and a lot of applications as I describe here. However, running the compute-intensive DNN on IoT device is quite challenging. So mainly because of the limited computing resource and harsh deployment environments of IoT device. So one promising solution is to sort of offload DNN inference tasks to the powerful edge servers and then send raw video or image data over networks. However, in this scenario, wireless loss hub can become a bottleneck, and IoT device has to aggressively compress the source data before they send out. Obviously, compression can help, but they also have some limitations. Our experimental result on semantic segmentation shows that lossless PNG compressions produce more than 2 megabytes of file size, which is simply too large for edge inference architecture to scale. So next, lossy compression like JPEG can help reduce file size to a few hundred kilobytes, but at the cost of more than 8% of accuracy loss. So recently, there's a proposal of running DNN or using DNN to compress the data at source devices, but again, it incurred a heavy computation on source devices. These tables summarize these limitations of the compression technique today. So then what is the root cause of these limitations? We found that the root cause, these limitations actually comes from human-centric design of these compression techniques. The existing solutions make the compressions artifact invisible to specific to human eye, or more exactly the perception sensitivity of a model. However, we found that DNN's perception model is very different from that of human eyes. So in these slides, we visualize the perception sensitivity of the one example DNN with respect to spatial frequency, and then we compare that against that of human eyes. As you can see, there are significant differences. Some spatial frequency might be sensitive to human eye, but not to deep neural networks. Then the question is, can you make sort of the compressions aware of these DNN characteristics? So our answer is yes, and then we propose a solution called GRACE. So GRACE has 3 design features. So first, GRACE model the DNN's perceptual sensitivity with respect to spatial frequency and then color space by using some of the gradients from the deep neural networks. Second, GRACE can help reduce the traffic load without sort of harming the inference accuracy or with bounded loss. The third, our solution compress for the DNN, and then we reuse existing compression codec frameworks like the JPEG to achieve the low computing overhead and the IoT device and the good backward compatibility. Let's discuss design of the GRACE in a little bit detail. Our first design space is the quantizations in the spatial frequency. Existing image compression like the JPEG first take these raw images and then convert that images to the G-YUV color space for better compressions. And then use the discrete cosine transform, or DCT, to convert those images to spatial frequency representations. Here, DCT help concentrate most of information in a few low-frequency coefficients. Then the next step is to quantize DCT coefficients with a quantization table, followed by entropy encoding. Since human eye are sensitive to low-frequency DCT coefficients, the existing technique actually modeled the eye's sensitivity with respect to DCT spectrums, and then designed the quantization table from there. But because DNN have a different, has a different sensitivity, this requires different quantization table. So how can we do that? So to do that, we first need to model DNN sensitivity, right? The high-level idea here is that from the DNN perspective, compression can be viewed as adding a noise to the input images. And then gradients that we can calculate through this backward propagation actually characterize how much a small noise in the compressed input would affect the final loss in the deep neural network. Based on this observation, we propose to use a DNN's gradient with respect to the DCT coefficients as an indicator of its perceptual sensitivity. As shown in the left bottom figures, Grace can estimate sensitivity map that actually consists of the gradients with each and every DCT coefficients. Intuitively, if a DCT coefficient has a high gradients, it is considered important components for the inference, and then we compress less. So now, given the perceptual sensitivity map, how can we actually generate quantization table for the DNN? In a quantization-based compressions, an input image can be represented as n point DCT coefficients. So as shown in this green metric shape. In Grace, we extend this to include not only for DCT value, but also gradient from our sensitivity map, and try to customize quantization step to produce a quantization table. Now we can formulate this as some optimization problems. So I'm not going to explain the detail, but our objective here is to minimize this file size through this while these quantizations, subject to a constraint that extra DNN loss caused by this quantization should be bounded by given constant B. But our solutions, especially denoted as Q sub n, which is a quantization step, shows that larger gradients leads to the small quantization step and vice versa. This is exactly matching our intuitions. Now, next design space is with color sensitivity. Color images actually consist of 3 channels, red, green, and blue, and the human eye have a different perceptual sensitivity to each channels. This motivates the design of the G-YUV color space that is widely used to the user color model. So conversion from RGB to G-YUV format actually help concentrate most of the salient information to the Y channel, so that the other 2 channels, U and V, can be compressed more. Here, G-YUV is just a linear transform of RGB, and they are uniquely defined by 3 weights based on humanized perception model. So again, DNN perception model different, right? So then how can we do this? So we actually, in a Grace, we redesigned the YV color space for the DNN. Based on DNN's perceptual sort of the sensitivity or gradients as an input, we want to find optimal conversion weight that minimize the sensitivity and U and V channels. So what does that mean? Actually, this actually help quantize U and V channels more aggressively in quantization steps. So we evaluate the Grace over the various conditions, 2 computer vision tasks, 2 data set, and 6 compression formats, and the 6 DNN model. We use compressed file size and the inference accuracy as a metrics. So we first show the semantic segmentation result for both PNG and image Grace-based compressions. Top 2 figures shows the compressed image for both PNG and Grace. And we, as a human, we might be able to notice some compression artifacts from the Grace, meaning they compressed very aggressively. However, if you look at the figure in the bottom, which is the segmentation results, are almost identical, which means that DNN does not see the difference. Now let's look at the evaluations, comparing the Grace with the JPEG in a different quality level. So here, the larger number in Q, the higher quality. We use popular deep neural network, ERN22, for semantic segmentations task. We can see that Grace actually performed pretty well compared to JPEG in a different quality levels. For instance, the closest one is JPEG 95 that has actually they produce 40% larger file size, but 0.2% lower accuracy than grays. Finally, we evaluate grays in the image classification task over a large data set like ImageNet and the 4 different deep neural networks model. From the first table in the top, we can see that grays actually save up to 90% of the bandwidth compared to the raw data, and also it performs better than JPEG. This actually benefit comes with no accuracy loss, as shown in the bottom tables. So it actually is comparable to other DNNs inference loss, inference accuracy. So in summary, we propose grays. This is the first worked model, DNN's perceptual sensitivity with respect to spatial frequency and color sensitivity. And then we also show that grays enable data stream with a bounded loss. And then finally, we propose a design that actually grays can reuse existing compression frameworks to achieve low computing overhead for IoT devices and good backward compatibility. So in the paper, we have all the detailed algorithms and then a lot of exciting future direction as well. So with that, I will take a question.